Okay, so last term, we finished last term by looking at the normal distribution, and specifically, we front-ended that with a discussion of discrete versus continuous data. So just remember that discrete data is countable. It could be well, it is numerical, but it doesn't have to be whole numbers. But you should be able to count the numbers within the set, I suppose. So rolling a die, 1, 2, 3, 4, 5, 6, they're countable. Continuous data is not countable. It is a range of data, and what we need to do is we need to make room for the fact that there could be any sort of, we might have a data set with specific numbers in it, but we need to acknowledge or make room for the fact that there could be numbers outside of that. So, for example, length or weight. Your data set might have, good timing, Sunny, we've just started the theory part of it. The data set might have specific numbers in it, like 3.2 and 6.8 and 7.1, but we need to take into account that if it was lengths of something, then although 3.2 centimeters might be a length, so is 3.25 centimeters, so is 3.205 centimeters, etc. So it's continuous in that ultimately you can't count it. If we're looking at a distribution, a discrete distribution graph would look a little bit like this, right? This shouldn't be anything too amazing that I'm drawing. Maybe this is a weighted die. 1, 2, 3, 4. They don't have to be in order like this. They don't have to be whole numbers, but that's an example of a discrete data probability distribution graph. There are no points between 1 and 2. There are no points between 2 and 3, etc., etc. So we just have these points here, and to make the points stand out more, we draw lines up to them so that we can see that the probability of 2 is given by that point there. The probability of 5 is given by that point there. And if we were doing the probability of x greater than 4, then we would simply be saying it'd be, if you like, you could think of it like a length. It'd be that length plus that length plus that length. In other words, you'd look at the tops and say that plus that, for greater than 4, it'd be that plus that. It'd be 5 and 6. So what we're doing ultimately is we are summing the probabilities in order to get that that probability working. Okay, that's a discrete probability distribution. In a continuous probability distribution, we don't have the same capacity to draw these discrete lines because it's not discrete. So in continuous, we end up with something like this. Like that. So that's continuous. And we can look at a particular value here at 4, for example, and we can say that if I was looking at the probability of x greater than 4, then we would, in a kind of in a weird old way, what would we be doing is we'd be saying, if this was a continuous data, we would be saying everything past 4. Right? We would add up all those values. But of course, it's continuous, which means for every single line that I've just drawn, there's another line. So we get that. And between each line that I've just drawn there are more lines. There are more lines. And so we'd have to keep on adding up all of these lengths and keep on adding them up until effectively, what have we got? An area. Yeah, cool. So we end up with an area underneath the curve. And that is how we work out the probability of a continuous data, a random variable. Okay, does that make sense so far? It's the sum of an infinite number of little lines there. And if we sort of squish those lines up really close to each other, we end up with an area concept. Now, there's a bit of a weird anomaly, which I'm going to write down then erase from your memory, because I don't think you really need to know other than just to be.
I don't have an answer for that.
I'll stop it, Siri. Is that if this is an area, if the probability of a continuous random variable is an area, then it turns out that if I look at the probability at a specific point, like x equals 4, then I get a DNE kind of thing. It does not exist. At a specific point, we would have a single line, and a single line doesn't have an area. And therefore, if it doesn't have an area, I can't work out the probability distribution for a particular point. So it's a bit weird in that sort of regard. If you, for those of you who have watched the videos, you'll see a slightly different explanation as well, where they talk about the probability at x equals 4 doesn't exist because there are variations to either side of x equals 4 and all this kind of stuff. Okay, the next thing I just wanted to point out so that it was nice and clear, that when you see the word PDF, it means probability distribution function. And the graphs there on the left-hand side in slide 1 there are 2 examples of probability distribution functions. I don't know what those functions are, but you could technically model them. You can have a discrete function. It's just a series of lines like you've got there on the left there. Or what you're used to when you see functions is you're used to seeing continuous functions where you have a smooth line that may or may not be curved, and that is also a function. So the point I just want to make here is that anything could be a probability distribution function. So we could have a probability distribution function that looks like this. Okay? Yes, thank you, Kian. And I was about to say, I'm not saying that everything is a probability distribution function. I'm saying that the probability distribution function could look like anything. But you're right, we do have some limitations. And the main limitation is that area. Let's see if I can get you to figure that out. That area must be equal to a very specific value. Go for it. Yep, 1. Thanks, Hamish. The area must equal 1. So if you can come up with a function so that the area underneath the curve for a given set is equal to 1, then you're good to go, right? Could that include negatives? Yeah, it could do. It's going to be above the x-axis, though, for reasons that will be clear when we do a unit called integration. But ultimately, if we can have an area underneath the line, between the x-axis and the line, equaling 1, then that could represent a probability distribution function of some description. It just so happens that we are looking at specific distributions, and they have their own specific functions. And for this course, you don't need to necessarily know exactly what that function is. But I wanted to reinforce, because it's really important for later maths, that they are effectively just functions. And the textbook does talk about them, but you don't need to know exactly what it is. The distribution that we looked at, or the distribution function, I suppose, that we looked at the end of last term was the normal distribution. We did a probability distribution, binomial distribution, which was a discrete distribution, and now we could look at a normal distribution. And the normal distribution looks like this here. Okay, so this is the normal distribution. So basically, if we've got a large data set, then we tend to find that the data settles itself into this kind of pattern here. Take, for example, all methods for students in Tasmania. Okay, they sit an exam and their mark is given for criterion 5. We tend to find for a very large data set that we'll have some people who do amazingly poorly, some people who do amazingly well, and everyone else is in between. Okay. Now, if I just took a sample set of this class, then it may be, well, this class, of course, will have a curve that sort of might be, have a really long tail here. That's so it's skewed to the left. So a really long tail, and then lots of people over here, because this is a highly intelligent class, right? So we would have not many people doing badly, and then lots of people doing amazingly well. Correct? Correct? Yes, 100%. Okay, so, but if we take the data set and make it really large, then we would expect overall people would be, some people do badly, some people do well, most people would do something in the middle. Okay, it's a normal distribution. That's what we call it. It's a normal distribution. So normal being regular. Not necessarily. So, for example, if we happen to write a amazingly difficult test in the exam, and then everyone does really badly, then you're going to get a skew anyway, even with a large data sample. Yeah. So you're going to get, you may or may not get a skew, but if we've done a pretty fair test, you'd expect it to be a normal distribution, if that kind of makes sense. Okay, just looking at properties of this normal distribution, if it's distributed normally, then you would expect the very, very middle, I won't do it in red, to be, just a reminder that that means the mean, like so. And that means that this side of the mean would represent 50% of the data, and this side of the mean would represent the other 50% of the data. And so you could say things like the probability that X is larger than the mean would be equal to 50%. Am I making sense so far? Tian. It's a bit tricky, that one, because we're talking about a continuous data set. It gets a little bit tricky. You can calculate, even though what I said before is, what I said before is technically the probability as of a specific value doesn't really exist on continuous data. However, what you can do is you can look at what the probability approaches. So what happens when the probability approaches the mean? So if someone got exactly the mean mark, as unlikely as that would be, could you work out the probability of it? Yes, you could, and we can use our calculator to give us the answer. But it's actually more to do with limit theory and saying, well, what value is the probability approaching as we look at a very, very small area either side of the mean? I don't think that's quite answered your question, but it's probably the best I can give under the circumstances. Yeah, looking at very specific means is a little bit different. Okay, so I shall brush past that and move on to the next slide. The next thing we need to consider with normal distribution, if it is normally distributed, then we tend to find the following facts. So I'm looking at slide 4 there. If we look at the distribution one standard deviation away, so that means plus, I'll just remember that sigma equals standard deviation, if you can't remember that. So plus or minus sigma, like so. Now the diagram's going to get very messy, so I'm not going to colour it in. But if we look at the area plus or minus one standard deviation away, then that would represent 68% of all values. Okay, it has been shown to be true that. If we look at 2 standard deviations away, so that's from minus 2 sigma to 2 sigma, so plus or minus 2 sigma covers 95% of all data. And if we look at 3 standard deviations away, like so, then plus or minus 3 standard deviations covers 99.7% of all the data. 99.7. That 0.2 is important. Okay, I'm going to show you as a picture in a second, but that's basically the 68, 95, 99.7 rule. Yep, from -3 sigma to 3 sigma. So what that means is that 99.7% of all data will be represented 3 standard deviations away from the mean. So if the mean was 10 and the standard deviation was 2, that'd be -2, -4, -6. So 10 minus 6 is 4, and 10 plus 2 plus 2 plus 2 is 16. That would mean that all data, 99.7% of the data would be between 4 and 16. That's how standard deviations work, right? It's how spread out the data is. The bigger the standard deviation, the bigger the spread of the data is. Am I making sense? Okay. Pictorially, I'm not going to draw this because they've already done it for me. Here we go. So this is, ignore the numbers here, but if 0 is the mean and this is 1, 2, or 3 standard deviations away, then we've got 68% covered here. 95% is covered between -2 and 2, and 99.7 is covered between -3 and 3. Of course, you can still get 4 standard deviations away or 5 standard deviations away, but that means they're in a very small percentage of the data. Okay, any questions? Alrighty, let's move on. I'll try and move on a little bit faster. We look at example 2 here. Then it says here, experience has shown that the scores obtained on a commonly used IQ test can be assumed to be normally distributed with a mean mu equals 100 and standard deviation sigma equals 15, beg your pardon. Approximately what percentage of the distribution lies within 1, 2, or 3 standard deviations of the mean? And so we can see here it says 68% of the scores will lie between 85 and 115. So you can see there's 100 here. So if I go 1 standard deviation down, I'd subtract 15. That gets me to 85. If I go 1 standard deviation above the mean, that'd be 100 plus 15. That's 115. And so I would have 68% would lie between 85 and 115. If I go 2 standard deviations down, that would be minus and plus 30. So that would be 100 minus 30 to 70, or 100 plus 30 to 130. So 95% would be between 70 and 130, and 99.7% of the scores would be 3 standard deviations away. So you'd subtract 3 lots of 15 or add 3 lots of 15 to get our interval here. Does that make sense? Yep, cool. In terms of a probability, guys, it'd be like, what is the probability of selecting someone whose IQ is between 55 and 145? Okay, so from the textbook there, we could see that, keep on going to the wrong tab, that 55 and 145 is 99.7. It's 3 standard deviations away. And so you would say the probability of selecting someone between 55 and 145 would be 99.7%. So you are almost definitely going to select someone whose IQ is between 55 and 145. You might not, but it's a very unlikely chance if you've got a big enough data set. Okay, I also wanted to note some symmetry about the normal distribution, and the symmetry property is this, is that if there's 95% between 2 sigmas away, like I've got here. I've probably made my sigmas a bit too far away. No, but that's for another lesson. So these 2 bits here would represent the other 5%, right? The bits in green. So green equals 5%, but the normal distribution is symmetrical, which means that each green bit is 2.5%. I'm a bit worried that there are some people that couldn't work that out. So it's just splitting up the difference there. 2.5% each tail there would make up the 5% in total. Okay, so just keep in mind that symmetrical property. Okay, let's move on a bit faster. I've got an example for you to write down. I'll zoom up just so you can write it down, and then we'll move on. When I go through this solution, I am going to be introducing you to sort of some language and concepts as we go along. So first things first is I would be, it's almost always worth drawing the situation here. So we just draw a horizontal line like the x-axis. We draw our normal curve in as best as you can. And we write in what we know about the graph, which is the average length. Good. So we put that in the middle there. That's mu. So mu is 30 centimeters. And so I'm going to write mu here. The other thing I'm going to do is I'm going to fill in what I need to know. I need to know the shortest 2.5%. So I need to know this value here. And that is going to be 2.5%. Now, by symmetry, I can see that tail here is also 2.5%, which means that the inside here is going to be 95%. Good news. If the bit in the middle is 95%, then if this is the value I'm looking for, let's call it little x. Is that going to be confusing? Let's call it k. Then k is going to be 2 sigmas away. Okay, 2 standard deviations away. Okay? So let's model that. This is how we write it. Let x be the random variable, r dot v, of tail lengths. Then x is distributed normally. That's how you write it. X is distributed normally with a mean of 30 and a standard deviation of 3.2, which makes the variance 3.2 squared. Okay, so you always write it down like that. You write it down with mean and variance. That's just a standard way of writing it. So I'll do that in red underneath so you can sort of see it. This is how you normally would write it. There's no need to calculate 3.2 squared. You can leave it as just 3.2 squared. In fact, I would say definitely just write it as 3.2 squared, because that way you've got the variance if you need it, just square the standard deviation. But you've also got the standard deviation explicitly written. Okay? So if you're given a normal distribution with, if it said n bracket 30 comma 4, then you know the standard deviation is 2, because 2 squared is 4. So it may or may not be written in square form, but you can always work it out. Okay, so the maximum length. Sorry. Oh, sorry, thank you. Yeah, I originally had it as 3.2, but then the numbers weren't as good. Good pickup, thank you, Sophie. 1.2. So the maximum length is going to be 30, the mean, minus, it's 2 standard deviations away. So it's going to be minus 2 times 1.2. 1.2 times 2 is 2.4. So that's going to be 30, 28, 27.6, I think. My mental arithmetic there has worked, I hope. Centimetres. There we go. So in other words, the maximum length, sorry, how do I put this? The biggest tail length that would be in that, the biggest tail length that would fit under this 2.5% is 27.6 centimetres. In other words, 2.5% of cats have tail lengths of 27.6 centimetres or smaller. Okay? That's what that means. Questions? So 30. So I shouldn't really call that k equals 2. That's probably a bit of a misnomer. I'm going to wipe that out. 30 is the mean. This is 95% of all data, which means that gives us the tail of 2.5%. This value k is 2 sigmas away from 30. So it's away from 30. It's below 30, so it's going to be 30 minus 2 lots of the standard deviation. So we've got 30 minus 2 lots of the standard deviation. No worries. Okay, so I'll get you to do some work now because I've been talking too long. So exercise 16B, and it's just a few questions to get you going. Questions 1, 3, 6, 7, and 8. So have a go at those, and then we'll have a look at some